Welcome back. In the previous video you saw how some matrices can be related to a diagonal matrix through a diagonalization. Such a relation can simplify computations, for example in the calculation of powers of a matrix. You also saw that not every matrix can be diagonalized. I'd like to address this issue in this video and show you criteria for diagonalizability of a matrix. First, let me return to the main result of the previous video. A matrix A can be diagonalized with invertible matrix P and diagonal matrix D precisely if the columns of P form a linearly independent set of eigenvectors of A, and D is a diagonal matrix of which the diagonal elements are precisely the corresponding eigenvalues. That is, the first diagonal element is the eigenvalue corresponding to the first column of P, the second diagonal element is the eigenvalue of the second column of P, etc. The important point is the following. We see that if an n by n matrix A has n linearly independent eigenvectors, then it is diagonalizable. The theorem here tells us how to construct P and D in that case, and P is guaranteed to be invertible because it has linearly independent columns. On the other hand, if A does not have n linearly independent eigenvectors, then it is not diagonalizable. Indeed, we could try to construct a matrix P, but if the columns would be linearly dependent, it's not invertible. This already gives a characterization of diagonalizability. Given an n by n matrix A, the following two statements are equivalent. 1. Matrix A is diagonalizable, and 2. There is a set of n linearly independent eigenvectors of A. Since the vectors lie in Rn, this set must in fact be a basis of Rn, sometimes called an eigenbasis. I will add more equivalent statements to this list in this video. First of all, the two statements given are equivalent to the following. The sum of the geometric multiplicities of the eigenvalues of A is equal to n. You may wonder how the multiplicities come into the game. Let me explain. First, remember that the geometric multiplicity of an eigenvalue is the dimension of the eigenspace. So statement 3 comes down to saying that the sum of the dimensions of the eigenspaces of A equals n. Let me show you in an example why this is necessary. Look at this 4x4 matrix A. To see if it's diagonalizable, let's try to find 4 linearly independent eigenvectors. I'll skip most of the calculations, you can check these yourself. Matrix A has this characteristic polynomial, here given in factorized form. You see that the eigenvalues are 2, 5 and 7. Following the standard procedure to find the eigenspaces, you get the following. All eigenspaces are one-dimensional. That means that all geometric multiplicities are 1, so they sum up to 3. Too small, according to the theorem. So why is this a problem for diagonalizability? Well, try to build a set of 4 eigenvectors. Each eigenvector must be contained in one of the eigenspaces. So each must be a multiple of one of the 3 basis vectors on the slide. That means that at least 2 of the vectors v1 to v4 are a multiple of the same basis vector. So the set of 4 eigenvectors is linearly dependent. The point is that since the dimensions of the eigenspaces don't add up to 4, there just isn't enough room for 4 independent eigenvectors. So indeed, the matrix is not diagonalizable. Now let's look at a situation where the geometric multiplicities do add up to n. Consider this 4x4 matrix. It is very similar to the example given before. The characteristic polynomial is in fact the same, and so are the eigenvalues. Let's look at the eigenspaces. E2 and E7 are again one-dimensional, but the eigenspace E5 is two-dimensional, so the geometric multiplicities add up to 4. This means that the matrix should be diagonalizable. Why is that? Well, we can make a set of 4 eigenvectors by simply combining the bases. As you can check, this set is in fact linearly independent, and this is no coincidence. For any matrix, the union of bases of the eigenspaces is linearly independent. So we found a set of 4 linearly independent eigenvectors, which means that the matrix is indeed diagonalizable. The two examples illustrate why the sum of the geometric multiplicities tells you whether a matrix is diagonalizable or not. Let's go back to the theorem. There is a fourth equivalence statement. For each eigenvalue, the algebraic multiplicity is equal to the geometric multiplicity. Let me illustrate how the algebraic multiplicities come in the context of the two examples. Remember that the algebraic multiplicity follows from the factorization of the characteristic polynomial. The matrices here have the same characteristic polynomial and therefore the same eigenvalues. The number of factors in the polynomial that corresponds to a given eigenvalue is the algebraic multiplicity of that eigenvalue. Here, the factors corresponding to eigenvalue 2 and 7 both occur once, so both eigenvalues have algebraic multiplicity 1 for both matrices. The factor corresponding to eigenvalue 5 occurs twice, so eigenvalue 5 has algebraic multiplicity 2. Note that in both cases the algebraic multiplicities add up to 4. This is not surprising. The sum of the algebraic multiplicities is the total number of factors in the characteristic polynomial, which is precisely the degree of that polynomial. And you have learned that for an n by n matrix, the degree of the characteristic polynomial is n, in this case 4. That means that the algebraic multiplicities add up to 4 for any 4 by 4 matrix. How does this compare to the geometric multiplicities? Remember the following inequality. For any eigenvalue, the algebraic multiplicity is larger than or equal to the geometric multiplicity. Now the algebraic multiplicities add up to 4, so the only way that the geometric multiplicities can add up to 4 as well is if for each eigenvalue both multiplicities are equal. And indeed, for the diagonalizable matrix B, for each eigenvalue, the geometric multiplicity is equal to the algebraic multiplicity. For the non-diagonalizable matrix A, the geometric and algebraic multiplicity of eigenvalue 5 are not equal. Let's return to the theorem. Statements 2, 3 and 4 each give a criterion for diagonalizability, something you can check to see if a given matrix is diagonalizable or not. Which one is the easiest to use depends on the matrix and the available information. I'd like to end the video with a useful consequence of the theorem. Let's look at the fourth criterion. Now remember that for each eigenvalue, the algebraic multiplicity is larger than or equal to the geometric multiplicity, which in turn is larger than or equal to 1. This means that if the algebraic multiplicity equals 1, the geometric multiplicity is 1 as well. In particular, the multiplicities are equal. So we get the following consequence of the theorem. If all eigenvalues have algebraic multiplicity equal to 1, then all geometric multiplicities are 1 as well, so the matrix is diagonalizable. This may seem like a very specific situation, but such matrices occur a lot. You can explore this theorem and its consequence in the exercises.